In this video, we will discuss how to predict products of single replacement reactions, specifically using the activity series. As you may remember, single replacement reactions occur when you have an ionic compound, such as what we have here with A, B, and then a single lone element. And that single lone element sometimes, not always, but sometimes is strong enough to go in there and break apart that ionic compound and then bond with one of the elements that was there. So for example, we've got element C. Element C comes in and disrupts the ionic compound AB and ends up bonding with A, and so we get the ionic compound AC. And then element B is kind of out of luck, and element B turns into its elemental form and is just left over. Okay, and so the way we predict if a single replacement reaction happens is using the activity series. Okay, so when I look at the activity series, let me point out a couple things that are really important to understand. It's a list, and elements that are at the top of the list are very reactive, meaning they can go in and break apart existing ionic compounds. And then elements at the bottom there, sometimes they can, but like, for example, gold. Gold is very unreactive, and so gold has a really hard time going in there and breaking apart ionic compounds. And so besides gold's cosmetic appearance, gold is a very valuable metal because it does not react with very many things. Okay, so that is how we want to read this. If I think about it even further, if I pick a random element here, so for example, magnesium. Magnesium is going to be strong enough or reactive enough to break apart an ionic compound that includes aluminum, zinc, chromium, iron, nickel, tin, lead, so on and so forth on this list. However, if magnesium comes across an ionic compound that contains lithium, potassium, calcium, or sodium, magnesium is not going to be strong enough to break apart that ionic compound. Okay? Also looking here, we've got to understand that this reactivity series is actually two of them. We've got the things that form cations, and those are mainly metals except for hydrogen. And then we have our elements that form anions, and those are essentially just our halogens as far as activity series are concerned. And so iodine, turns out it's not very reactive, whereas fluorine is very reactive. Okay, and so we've got to make sure we understand that there are two, because most of the time we'll use this left one, but sometimes we'll have to use that right one, and I'm going to give you plenty of examples in this video that use both. Okay, so let's go ahead and get started with some of these examples and see kind of how this all works. So in this first example, I have solid lead, and so that's going to be Pb solid. And I'm not worried about states of matter in this video. I will do states of matter, but it's not a priority for me whatsoever. And then zinc acetate, so we've got to be experts at naming ionic compounds. Zinc always forms a +2 charge, and then acetate is C2H3O2 with the -1 charge. And so we will need two acetates to cancel out the zinc. So we'll get C2H3O2, 2, and that's aqueous. So what we want to look at is if lead is strong enough to knock out zinc. So what I'll do is I'll come up here and I'll find lead, and I will find zinc, and it turns out lead is below zinc, so lead's not going to actually be strong enough to knock out zinc. And so this reaction will not occur, and so we'll just say no reaction, and we can abbreviate that no, RXN. And once that happens, just move on to the next problem. There's no point in trying to work with a reaction that does not even happen. Okay, on number 2, we've got solid iron, so that will be Fe solid, and that will try and react with aluminum oxide. Aluminum is Al plus 3, oxide is O2 minus, and so the least common multiple between those two is 6, so I will need 2 aluminums and 3 oxygens, and the problem tells me that that will be a solid. And so iron is going to try and knock out aluminum. So we'll do the same strategy. We'll go up to our reactivity series and we'll find iron, and we'll find aluminum, and iron is below aluminum. So that means iron is not strong enough or reactive enough to knock out aluminum. So this one is also no reaction. Okay, so we'll just move on. In question 3, we've got aqueous silver nitrate. That's Ag plus 1, and then nitrate is NO3 minus 1. And that is going to try to react with nickel. So we've got to write AgNO3, and that will be aqueous. That's going to try to react with solid nickel. And so I've got to see, is nickel strong enough that it's going to be able to knock out silver? So what I'll do is I'm going to go up to my list, and I'm going to find nickel, and I'm going to find silver. And it turns out that nickel is way above silver. So nickel is going to have no problem knocking out silver. So nickel is going to come in and just trade places with silver. And so what we'll get is we're going to get just pure silver. So that's kind of nice if that's what you wanted. And then we're also going to get nickel nitrate, but this problem says specifically Ni plus 2 is the ion. So we will need 2 nitrates to cancel out the Ni plus 2. And I know that that will be aqueous, but again, not my concern. And so then again, to balance this, I'll just finish that off like so. And that is how you do a single replacement reaction. Let's look at number 4. Number 4 is a pretty good problem. We've got sodium bromide, and so sodium is Na plus 1 according to the periodic table. And we've got bromide, which is Br minus 1, again, according to the periodic table. So that will just be NaBr. That will be aqueous. We're going to try to react it with solid iodine. What a lot of students will do is they're going to put just I, but we've got to remember our 7 diatomic elements, and I use the phrase Brinkelhoff to remember those. And iodine is one of those. And so this is actually I2, okay? And then this one's a little bit different because we want to see, is iodine strong enough to knock out bromine? Remember, halogens only knock out halogens. Okay, maybe we write that down because that's really important. Halogens can only, oh, my spelling is off, only knock out other halogens. Okay, that's really important. A lot of chemistry students will try to take iodine and replace sodium with iodine, but that is not what will happen. So what I have to do is I have to go up to my activity series, but use my one for halogens, and I'm looking at iodine and bromine, and it turns out iodine is not going to be strong enough to knock out bromine because iodine was less reactive. So this will just be no reaction. And I'll move on, and we can look at number 5. We've got aluminum bromide. Aluminum is Al plus 3. Bromide is Br minus 1. So I'll get AlBr3, and that will be aqueous. And then chlorine is also a diatomic element, so that will be Cl2. And what I have to do is I have to see, is chlorine going to be reactive enough to knock out bromine? So let's go to our activity series. And I've got chlorine and I've got bromine, and it turns out chlorine will be reactive enough so we can go through on this reaction. And what I'll end up with is aluminum chloride. That will be AlCl3. I know that that is aqueous. Plus the element bromine, which we just finished talking about, is diatomic, so that will be Br2, and that will actually be liquid. Bromine is one of only two elements, the other one being mercury, that's a liquid at 25 degrees Celsius. And so to finish this off, I'll just get this guy balanced, and that will actually be 2, 3, 2, 3. Okay, let's just do one more, and let's do number 10. Number 10 is a great example because it has some things that a lot of chemistry students mess up on. And so we've got solid potassium, that will just be K, solid, plus liquid water, and I'm going to write water as HOH in a single replacement reaction, okay? Because that's going to help me see that potassium is going to try to knock out only one of the H's in water. So we've got to go up to our activity series and see, is potassium more reactive than hydrogen? And when I do that, potassium is here and hydrogen is here, and potassium is actually one of the more reactive elements on the periodic table. And potassium is not going to have any problem reacting with hydrogen. And so potassium will come in there and knock out one of the H's. And so what we'll end up with potassium plus 1, hydroxide OH minus 1, and we'll end up with potassium hydroxide, which will be aqueous. And then we'll end up with just the element hydrogen, but hydrogen is a diatomic element. Remember, it's in one of those Brinkelhoffs. It's in that list. So this will actually be H2 gas. And then to finish this one off, I just want to balance it. And so to balance it, I'll just put a 2, 2, 2, and we should be good. And so that's just the basics of how to balance and how to predict the products of single replacement reactions.